What if the very concept of a beginning is flawed? What if the universe didn't start in time, but with it? Imagine a fire so blinding it doesn't burn, a roar so loud it's silent, a moment that doesn't come after anything because nothing existed for it to follow. No matter, no space, no time, just a strange flicker, less than a flicker of becoming. And from this absence, from a place without place, the cosmos bloomed, not into the void, but into itself. Not onto a stage, but into the stage's creation. This is not myth, this is physics. This is the birth of reality. Please like and subscribe because this journey will change how you see our place in the universe. Prepare yourselves. We begin. In the deepest silence imaginable before the word before meant anything, something changed. There was no audience, no witness, no fabric of reality to record the transformation. But it happened. A singularity, infinitesimal and infinite at once, appeared without a where or a when. It did not explode in the way fireworks rupture the night. It unfolded, blooming like a fire born of thought, not fuel. The Big Bang was not an explosion inside space, but the sudden appearance of space itself, stretching, expanding, pregnant with all possibility. The galaxies did not scatter across a void, they were carried by the growth of the void itself. This is the paradox we inherit, that the entire observable universe, billions of galaxies, each with billions of stars, was once compressed into a point so small that the word small becomes meaningless. A dimensionless origin, a singularity, not just dense and hot beyond comprehension, but a place where the laws of physics, our precious, tested rules, collapse. The singularity is not just a curiosity, it is a wall, a warning. It says, beyond this point, your understanding breaks, and from that unknowable brink, reality as we know, it surged forth. We cannot speak of a time before it, not because we're limited in tools, but because before may have no meaning at all. Time was born with the bang. There was no ticking clock counting down to it. There was no waiting. Time itself began its forward march. Only once space had room to expand. It is a haunting realization that everything we experience, every moment, every heartbeat, every orbit, all emerged from a momentless moment. Asking what came before the Big Bang is like asking what's north of the North Pole. It's not that the question is foolish, it's that the geography of existence doesn't allow the answer, and yet someone saw it coming. Georges Lemaître, a Belgian priest and physicist, looked into the equations of Einstein's general relativity and saw something extraordinary. The universe, he realized, could not be static. It had to be changing, growing, or shrinking, never idle. He imagined the ultimate rewind, galaxies rushing inward, stars collapsing into gas, atoms shattering into energy, until all of existence was a single, seething point. He called it the primeval atom. In a universe clinging to the idea of eternal stillness, his vision was revolutionary, so much so that even Einstein, the architect of the very mathematics Lemaître used, dismissed the idea. Your math is correct, he admitted, but your physics is abominable. The idea of a beginning felt too mystical, too spiritual. The cosmos was supposed to be endless, timeless, safe. Even ridicule followed. The English physicist Fred Hoyle, firmly devoted to the steady-state model, a universe eternal, with no beginning and no end, mocked the idea by calling it the Big Bang. He said it on BBC Radio in 1949, intending it more as a joke than a label. But history has a sense of irony. The name stuck, becoming the banner of modern cosmology, while Hoyle's own model was gradually swept aside by mounting evidence. But Lemaître had lit the fuse of a new understanding, an understanding that from a state beyond comprehension, reality had emerged in a blaze. Not with fanfare, not with thunder, but with the quiet birth of space itself. In that instant, everything changed. Time began its long journey. Energy and matter danced their first steps. The seeds of stars, galaxies, and life were scattered into a formless soup of creation. And now, nearly 14 billion years later, here we are shaped by that same event. We stare into the heavens, collecting the faintest echoes of that birth. We point our telescopes into the past. We study the light still traveling from that first instant, and we try to piece together the moment when the universe caught fire, not from outside, but from within. Not in a place, but as the place itself. We are made from that moment, from that heat, from that singular nothing that became everything. You, reading this now, are composed of atoms forged in stars, themselves descendants of hydrogen born in that primal blaze. And if we trace the story of those atoms back far enough, they were once indistinguishable from the fire that gave rise to time itself. You are not in the universe, you are of it. You are a ripple in the wave that began at the beginning. You are what the Big Bang became 8 billion years later, asking itself what it once was. How long is a second? Long enough for a thought, a breath, a choice. But what if we told you that in the first second of the universe's life, everything that matters, everything that makes matter had already been set into motion? That within less than a blink, less than a thought, less than anything we can intuitively grasp, the universe didn't just exist, it evolved. It unfolded like a miracle dressed in mathematics. From a point smaller than a proton, it expanded to something unimaginably vast. And from this expansion came not just size, but law, force, order, symmetry, and the first hints of becoming. Time zero. The clock starts not with a tick, but with an unknowable shiver. The Planck time 10 to the power of negative 43 seconds after the beginning. If that number means nothing to you, that's because it shouldn't. It's smaller than meaning itself. A decimal point followed by 42 zeros and then a 1. At that threshold, time, space, energy, and gravity are stitched together so tightly that our physics can't see in. It's not darkness, it's blindness. Our most sophisticated equations, quantum mechanics, and general relativity clash like titans at the gate. They both work perfectly in their own domains, but together, at this edge of reality, they unravel. And yet, something happened there, something monumental. Because by the time that first tick ended, the universe wasn't just a fireball, it had already begun laying its blueprints. The forces we now call gravity, electromagnetism, and the strong and weak nuclear forces, they were not always separate. In those earliest moments, they were unified. One elegant superforce, humming with symmetry, no cracks, no distinctions, a perfect crystal of power. But as the cosmos cooled by the tiniest degree, that symmetry shattered. Gravity fell away first, drifting off as the weakest but most far-reaching force, shaping the arcs of galaxies and the falling of apples alike. Next came the strong force, the glue that binds protons and neutrons. Then the electroweak force split into two, electromagnetism, which lights our cities, and the weak force, which fuels the Sunday. 4 siblings born from one parent divided by the cooling breath of an expanding universe. Imagine dropping a single drop of dye into a still ocean, and in an instant, the color spreads across the cosmos. That's what happened next. An event so staggeringly fast it defies comparison. Cosmic inflation. In less than a trillionth of a second, the universe expanded by a factor so vast that it would take 1,000 digits to write down. At 10 to the power of negative 36 seconds old, the universe was smaller than an atom. At 10 to the power of negative 32 seconds, it may have been larger than the observable universe today. And this wasn't just swelling, it was space itself stretching. Not objects moving through space, but space moving objects. Galaxies weren't flying outward, they were being carried, like crumbs on rising dough. A repulsive form of gravity, yes. Gravity that pushes instead of pulls was driving this expansion. The vacuum of space, infused with a special kind of energy, acted like a cosmic fuel line. Einstein's own equations allowed for it. He called it the cosmological constant, and later regretted it. But here, in the baby universe, it was the engine of growth. Inflation didn't just make space big, it made it flat. It ironed out the wrinkles. It hid the chaos behind a curtain of scale, and most importantly, it seeded the story to come. Because during this mind-shattering expansion, quantum whispers were frozen into place. The tiniest, most random fluctuations, just uncertainty dancing at the edge of nothingness, got stretched across the universe. Microscopic jitters became macroscopic fingerprints, the very seeds of structure. Where one patch was just slightly denser, gravity would tug harder. Where one area had a little less, matter would drift away. These were the embryonic shapes of everything: galaxies, stars, planets, us. The order we see in the night sky began as a ripple in a quantum foam, written into the fabric of space, like a poem only gravity could read. And then, as abruptly as it began, inflation stopped. Its repulsive energy released into the infant universe like a thunderclap. Space, now vast and flat, lit up. The energy that drove the expansion was dumped into the cosmos, transforming into particles, quarks, gluons, electrons bubbling in a primordial soup at temperatures exceeding 10 billion degrees. Matter was no longer an idea, it was real, forming in clouds of chaos and heat. Protons and neutrons flickered into being, danced with electrons, and collided in waves of high-energy fury. The universe, 1 second old, was hot, dense, bright, and alive with creation. In those first few minutes, nuclear reactions began. Protons and neutrons collided and fused, forming the first atomic nuclei, hydrogen and helium, in the exact proportions we still observe today. That early chemistry was no accident. It was a fingerprint, a prediction from the Big Bang theory, later confirmed by telescopes. This wasn't just guesswork, it was alignment between math and matter, between theory and sky. But for all its light, the early universe was not transparent. Photons, particles of light, couldn't get far. Electrons were still free, bouncing around and scattering every ray of light like fog in a storm. The cosmos was brilliant, but blind, glowing, but opaque. This fiery fog would endure for hundreds of thousands of years, a brilliant sea of energy, where light and matter danced in tight embrace. And yet, even in this chaos, ripples persisted, tiny variations in density, born from quantum randomness, pushed and pulled matter and radiation into waves, literal sound waves, moving through the plasma of the universe. These acoustic signatures, these vibrations of the newborn cosmos, would leave behind faint patterns. Later, they'd show up in the afterglow of creation itself. But for now, the universe remained cloaked in light, too tangled to escape. The first second passed, a heartbeat. And in that heartbeat, the forces of nature were born, the particles of matter assembled, the symmetry of the universe shattered into beauty. From something smaller than nothing, a foundation had been poured, and every star, planet, and living being that would ever exist was written into that first moment like a code etched in fire. We now look back across 13.8 billion years and realize we are not latecomers to the story. We are its continuation. We are its witnesses. We are its questions, walking and breathing. Light is freedom, but for the first 380,000 years of existence, light was a prisoner. Born in a universe blazing hotter than a star's core, it struggled to take a single step without being struck, scattered, stopped. Imagine a world where every photon was trapped, where light itself could not move forward. A cosmos glowing so bright, it blinded itself. This was the early universe, not darkness, but a brightness too tangled to see, a fog of fire. And then, one day, it cleared. The first window opened, light was freed, and that ancient freedom still reaches us, whispering the story of our birth. The universe, still an infant, had spent hundreds of thousands of years as a thick, churning ocean of plasma particles colliding endlessly, energy ricocheting in every direction. Photons, the carriers of light, were caught in a cosmic pinball machine, scattered by free electrons at every turn. The temperature hovered around 10,000 Kelvin, far too hot for atoms to form. Protons and electrons existed, but not as partners. They were free-floating charges, repelling, colliding, never resting. Light tried to move but couldn't. It was like trying to run through a crowd where every step triggered another collision. This wasn't darkness as we know it. It was brilliance caged by chaos. But expansion is patience in motion. As the universe stretched, it cooled, slowly, relentlessly, like breath escaping into night. And then came the moment, the quietest revolution in cosmic history. Around 379,000 years after the beginning, the temperature dipped to about 3,000 Kelvin. It was still unimaginably hot by human standards, but just cool enough for something magical to happen. Electrons and protons, once enemies, found peace. They joined to form hydrogen atoms, stable and neutral. No longer free to scatter light, they stepped aside. The fog lifted. This event, known as the Epoch of Recombination, changed everything. Suddenly, the universe went from opaque to transparent. For the first time, light could travel. Photons, unshackled from the chaos, streamed freely in every direction. That first light is still traveling, stretching across the cosmos for 13.8 billion years. We see it today as the cosmic microwave background, a faint afterglow that fills the sky like the memory of creation. It is the universe's first photograph, a baby picture, written not in ink but in radiation, cold now, barely 2.7 Kelvin above absolute zero, but unmistakably there, a ghost of the original blaze. And yet, this light is not smooth. It's dappled, speckled, freckled with tiny variations in temperature and density, 1 part in 100,000. In those subtle splotches lie the echoes of quantum fluctuations, magnified by inflation and imprinted on the newborn cosmos. Where the glow is slightly warmer, matter was slightly denser, and where it was denser, gravity began to tug a little harder. These gentle variations were the seeds of everything. They were the blueprint for galaxies, for stars, for the spiral arms of the Milky Way, for the gravity that would eventually pull dust into planets and planets into purpose. This cosmic background radiation isn't just a relic, it's a map, a fossil, a song frozen in time. If our eyes could see microwaves, the night sky would shimmer with this ancient light. It's everywhere, all around us, every direction. In fact, when you tuned an old television to static between channels, a few percent of that white noise was CMB, literally, the hiss of the Big Bang, the universe singing its origin in a language older than atom. But in those first moments of transparency, something else was happening too. The universe wasn't just cooling and clearing, it was listening. As the fog lifted, the pressure waves that had once rippled through the plasma now left behind their fingerprints. Acoustic oscillations, sound waves in the early universe, etched patterns into the matter itself. Like cymatic shapes on a drumhead, these vibrations sculpted the large-scale structure of the cosmos. Where matter clumped, stars would one day ignite. Where it thinned, great voids would expand. It was the beginning of structure, the first hints of architecture in a universe that had, until now, only known fire. The beauty of this moment is not just in what it created, but in what it revealed. For the first time, the cosmos could be seen. Not by any eye, of course. There were no eyes yet, but the potential was born. The universe had made itself visible, it had become knowable, and the light that began that journey, those first liberated photons, have never stopped traveling. They are still coming, still arriving, still telling the tale of that moment when matter calmed, light escaped, and the universe for the first time opened its eyes. And so began a long silence, a dark waiting. For though light was free, stars had not yet been born. The universe was now clear, but empty of fire. The cosmic dark ages had begun, a time when the hydrogen fog drifted silently through the void, cooling, coalescing, hiding its potential like a dream not yet remembered. But deep within those clouds, gravity waited, pulling, gathering, preparing to ignite the next chapter. The universe had taken its first breath. It had seen its first light, and in that light, it had already written the story of all things to come. What happens after light is born, but before anything shines? Imagine a universe filled with perfect silence, Not absence, but anticipation. No stars, no galaxies, no glowing suns, just darkness. A darkness that is not dead, but sleeping. Hydrogen and helium drift, like invisible winds across a cooling canvas, waiting. The fog has cleared, but the cosmos has not yet learned to spark. Time stretches, gravity whispers, and somewhere in the stillness, a promise is being made that soon something will burn again. This is not the end of light, but the moment it retreats, so it can return brighter, fiercer, and alive with fire. The light of the cosmic background had spread in all directions, and with it came silence, not because there was nothing, but because nothing yet spoke. The universe had become transparent, but it was still dim. It was open but empty of stars. For millions of years after recombination, hydrogen and helium, those firstborn atoms, floated in vast, cooling clouds. The heat of creation had faded into a dim microwave whisper. No stars blazed, no planets spun, no structures moved in their own light. The cosmos had grown cold, still, waiting for something to gather, to collapse, to ignite. We call this time the cosmic dark ages, but it was more than darkness. It was the long inhale before a universe could sing. And yet, even in that quiet void, gravity had already begun its patient labor. Though the matter was thinly spread, it wasn't perfectly smooth. The tiny fluctuations in density, those fingerprints left behind by inflation, were enough. In some places, gas gathered ever so slightly. In others, it drifted away. Over time, these differences were magnified. Denser regions began to draw more mass. Clouds thickened. Pools of hydrogen began to collapse under their own weight. There was no light yet, no stars, just gravity silent, tireless, pulling the threads of structure into place. Hundreds of millions of years passed, but the universe had time. And finally, in some of those densest knots of hydrogen, pressure and temperature reached a critical point. The atoms, crushed by gravity's embrace, fused, and in that fusion, the first stars were born, sparks in the void, flickers of fire across a black ocean. These were not stars like the ones we see now. These were giants, monsters of fusion, hundreds of times more massive than our sun, burning fast and dying young. Their light cut through the darkness like knives. Their energy transformed the surrounding gas, ionizing it, heating it, reawakening the fog. The Dark Ages were ending. This was the dawn of the Epoch of Recombination, a time when starlight began to punch holes in the hydrogen mist, clearing pathways for light to travel once more. The universe, once a glowing fog, had become dark, and now it was becoming luminous, not just transparent, but illuminated. These first stars didn't last long. They lived just a few million years before detonating in colossal supernovae, explosions so violent they tore themselves apart. But in their deaths, they sowed the seeds of everything to come. For while the Big Bang had created hydrogen and helium, these stars created everything else: carbon, oxygen, iron, the ingredients of planets, of oceans, of bones and breath and thought. Their remnants collapsed into black holes. Their ashes seeded new clouds. And from those clouds, new stars formed, smaller, longer-lived, surrounded by disks of dust and rock. Galaxies began to swirl into being, drawn together by invisible strands of dark matter, not randomly, but according to a grand hidden pattern. The early universe didn't grow like chaos, it grew like a web. Filaments of galaxies stretched across vast gulfs, forming structures so immense they defy our senses. Clusters and superclusters, walls and voids, a cosmic architecture shaped by gravity and time. By around 200 million years after the Big Bang, this great transformation was fully underway. The first galaxies lit the sky, not just stars scattered in the dark, but cities of light, collections of suns, orbiting one another, held by shared mass and shared fate. The universe was no longer just a stage, it had become a story. From formless clouds to spirals and clusters, the cosmos had begun to organize itself. Order was rising from fire, beauty was emerging from noise. And somewhere, buried in the quiet math of all this unfolding, was a promise written in hydrogen and helium, that one day stars would form planets, planets would harbor oceans, oceans would birth chemistry, and chemistry would begin to question the stars, that from this long darkness, minds would awaken, that consciousness would be a late echo of fusion, that the universe, once blind and burning, would eventually look back on itself and ask how it all began. But in that first dawn, there was no question yet, only fire, only light, only the long-awaited return of the stars. Imagine stepping back so far from the universe that its individual stars disappear, its galaxies blur, and its structure becomes visible like strands of cosmic silk. Now imagine those strands forming not randomly, but with rhythm woven by invisible hands of gravity, time, and ancient light. Beneath the chaos, there is order. Beneath the fire, a blueprint. What began as quantum tremors, magnified by inflation and sculpted by gravity, has become a lattice of galaxies, a cosmic web that stretches across billions of light years. From a singular blaze came elegance, from formlessness came design, and we, floating inside it, are only beginning to see the pattern. Galaxies didn't emerge like dots on a map. They followed trails, clustering where gravity had once gently favored one ripple over another. The slightly denser pockets of matter left behind by inflation, barely distinguishable at first, acted as seeds for structure. Over billions of years, these subtle hints were amplified. Gravity pulled gas into stars, stars into galaxies, galaxies into clusters. The result is a vast cosmic web, tendrils of light and mass stretching across unfathomable voids, like the filaments of a spider's web spun in the darkness of space. This wasn't random. It was music, playing on the strings of spacetime, guided by notes written in the earliest seconds of existence. And yet, even as structure grew more complex, a strange simplicity emerged. Look far enough, wide enough, deep enough, and the universe becomes smooth, homogeneous, the same in every direction. It's a paradox. Immense detail nested within vast uniformity. A galaxy here, a galaxy there, but on the largest scales, a kind of serenity emerges. This cosmic uniformity was once a shocking discovery, because for a universe to look this smooth across billions of light years, it had to have been connected at the start, in those impossible early moments before even light could travel. That mystery is what inflation resolved. It stretched the early universe so rapidly, so thoroughly, that any irregularities were ironed out, and the same conditions were smeared across the cosmos. That's why the universe appears so balanced now, so consistent even though it's been growing and aging for nearly 14 billion years. We have tested this vision not just with math and maps, but with light, with machines that see farther than any human eye. Our telescopes peer into the depths of space, and by extension, into the depths of time, because light takes time to travel. Looking far means looking back, and what we see confirms the story. Galaxies younger, smaller, more chaotic in the early universe, clusters forming, voids expanding. We have mapped their distribution across the sky and found the fingerprints of that original inflationary whisper laid out across the heavens like a fossilized breeze. The real breakthrough came when we stopped just looking and started listening. In 1989, NASA launched COBE, the Cosmic Background Explorer. It was the first to truly measure the temperature ripples in the cosmic microwave background, the faint, leftover light from recombination. What it found was astonishing. In that glow, it detected tiny variations, 1 part in 100,000, just as predicted. These weren't imperfections, they were signatures. The echoes of quantum fluctuations stretched by inflation, encoded in the sky. George Smoot, the mission's lead, famously said, "If you're religious, it's like looking at the face of God." What he meant was awe, pure, scientific awe, at the clarity of the cosmos' own memory. COBE was just the beginning. In the early 2000 seconds, the Wilkinson Microwave Anisotropy Probe, WMAP, took over, sharpening our view of that infant light. WMAP didn't just see the ripples, it measured them with 30 times more precision. The patterns weren't random. They matched the exact statistical predictions made by cosmological theory. Where theory said a bump should be, a bump was found. Where silence was expected, silence reigned. And then came Planck, the European Space Agency's next-generation satellite, refining the map even further. Planck revealed that the universe is 13.8 billion years old, with space so flat that it defies curvature. It confirmed that the cosmos is made mostly not of atoms but of mysteries, dark matter, and dark energy. And all of it, stitched together, matched a story that began in the smallest of instants. In those beautifully imperfect splotches of the microwave sky, we found a Rosetta Stone for reality. The acoustic waves that rippled through the early universe are still imprinted there, forming peaks and troughs in the spectrum of temperature variations. These oscillations, frozen sound, have helped us decode the size, shape, and fate of the cosmos. They are not just proof of the Big Bang, but proof of the subtle and surreal events that immediately followed it. That's the power of modern cosmology, to match theory not just in spirit, but in decimals. And so, the universe has revealed itself not as chaos, but as choreography. From quantum randomness came cosmic rhythm. From heat, harmony. The filaments of the cosmic web stretch like veins through the dark, pulsing with galaxies, each one home to billions of suns. We live on one tiny rock orbiting one of those suns, in one spiral arm of one galaxy. But the story of how we got here was written across the entire universe, etched into the first, second, amplified by gravity, preserved in light, and now measured with care. That we understand this is nothing short of miraculous. That we can model it, test it, and see it confirmed in the sky is a triumph of human curiosity. We have gone from wondering at the stars to tracing their ancestry. We have built instruments that listen to the afterglow of time's birth and find in it the fingerprints of everything that would come. And so we stand here, on the edge of knowledge, peering out into a universe that has become comprehensible, not simple, not finished, but legible. And the more we understand the pattern, the more we realize it's not random, it's not arbitrary, it is the echo of a beginning so precise, so powerful, that it left nothing untouched. Sometimes, the universe reveals itself not in explosions, but in shifts so subtle they hide in plain sight. Imagine staring at the sky and believing it's eternal, fixed like a painting. Now imagine realizing the painting is stretching, expanding, swelling outward with time. Not a metaphor, but a measurement, a red blush in the spectrum of distant galaxies, like the Doppler effect of a cosmic siren moving away. This was the whisper the stars had been sending all along, and in one quiet moment, a man with a telescope caught it. That was the moment the universe stopped being still and became alive. In the early 20th century, the prevailing view among scientists and philosophers alike was that the universe was static, unchanging, eternal, held in perfect balance. The heavens were thought to be a silent dome, hung with unshifting stars and swirling clouds of gas. The spiral nebulae, those ghostly smudges on photographic plates, were believed by many to be small, local curiosities within the Milky Way. The idea that these glowing spirals could be other galaxies, separated by vast gulfs of space, bordered on the absurd. But truth, as always, was waiting in the data. In 1929, Edwin Hubble changed everything. Working with the 100-inch Hooker telescope at Mount Wilson Observatory, he studied those spirals not just for their shape or brightness, but for their velocity. Using the redshift of their light, how the wavelengths were stretched toward the red end of the spectrum, he measured how fast they were moving. And to his astonishment, every single galaxy he observed was receding. Everyone. Not only that, but the farther a galaxy was, the faster it was fleeing. This wasn't a coincidence. It was a law, a linear relationship between distance and velocity, now called Hubble's law. The universe wasn't static, it was expanding, and that changed everything. Suddenly, Lemaître's radical idea of a primeval atom, a universe with a beginning, was vindicated. The math had always suggested it, but now the sky agreed. If galaxies are flying apart now, logic demands they were once close together. Trace that motion backward, and you arrive at a single, dense point. Not metaphorically, but mathematically. The Big Bang stopped being speculation. It became the best explanation. But the story wasn't done proving itself. Decades later, in the 1960 seconds, two engineers at Bell Labs, Arno Penzias and Robert Wilson, were fine-tuning a microwave antenna, trying to eliminate a persistent background noise. No matter where they pointed it, the hiss remained. They cleaned the equipment, chased down every possible interference, even removed a pair of nesting pigeons and their droppings from inside the antenna's horn. Still, the noise stayed. It was isotropic, coming from every direction, all the time, with equal strength. At first it was an annoyance, then it became a revelation. Unbeknownst to them, just 30 miles away, a team at Princeton led by Robert Dick had been searching for this very thing. Years earlier, theoretical physicists had predicted that if the universe had indeed begun in a hot, dense state, it would still be glowing with the afterglow of that heat stretched by expansion, cooled to microwave temperatures, but still present. That faint background radiation would be the smoking gun of the Big Bang, and Penzias and Wilson had stumbled into it by accident. The moment the two teams connected, cosmology took a quantum leap forward. That low-level hiss, later named the cosmic microwave background, was the embers of creation. The final photons, from the hot plasma, set free during recombination, still arriving at Earth after traveling across time. Measured at about 3 Kelvin, just a few degrees above absolute zero, this ghostly light was exactly what the theory had foretold, the afterglow of the fireball, the radiation from the moment light first escaped, the confirmation that the universe really had begun in heat and light. Penzias and Wilson were awarded the Nobel Prize in 1978, not for discovering a new force or particle, but for hearing the oldest sound in the universe, the quiet hum of everything beginning. And so, with Hubble's expanding galaxies and the CMB's pervasive whisper, the Big Bang shifted from theory to narrative, a story told in red light and radio waves. The cosmic clock didn't just start. We could now read it. We had distance, we had velocity, we had temperature, and when all these numbers were put together, they pointed not just to a universe that had a beginning, but one that remembered it. The implications were staggering. If the cosmos was expanding, then it had once been smaller, hotter, simpler. And if there was a time when all matter and energy were crammed into an incomprehensibly small space, then something extraordinary must have happened to let it grow. The theory didn't answer every question, but it answered the most important one. Was there a beginning? And the answer, increasingly, was yes. We now live in a time when telescopes and satellites can see across billions of light years, peering back through time like archaeologists of the stars. Every observation, from the movement of galaxies to the glow of ancient light, tells the same story. We live in a universe that began in fire, stretched into structure, and continues to grow. It is not a static painting. It is a moving, breathing history. And somewhere inside it, on a tiny blue planet, orbiting an average star, a species emerged that could listen to the whispers of the beginning and understand. Before there were stars, before there were planets or people or questions, there was only heat. But even in that heat so blistering it blurred the boundary between particle and light, a kind of order emerged. Imagine the universe as a roaring furnace, yet somehow already knowing how to build. No hands, no designer, just laws, and from those laws, a recipe. A few minutes after the birth of time, a silent alchemy began. The first elements were forged, not in the heart of stars, but in the heart of the universe itself. A chemistry without chemists, a blueprint without blue ink, a miracle that needed no miracle. It happened quickly. By the time the universe was a mere few seconds old, it had already cooled from unimaginable temperatures to something merely hellish, billions of degrees. Protons and neutrons, formed in the chaos of the first second, were now free to find each other. No stars yet burned, but fusion had already begun. In this brief window, a few minutes long, the universe functioned like one enormous nuclear reactor. Light atomic nuclei collided, stuck, broke apart, and reformed. Hydrogen, the simplest and most enduring element, came first, then helium, its heavier and rarer sibling, a touch of deuterium, traces of lithium, and then the furnace cooled. This moment in cosmic history is known as Big Bang nucleosynthesis. It did not last long, but it defined the chemistry of everything. These first light elements were born in the universe's earliest fire, and their proportions, about 75% hydrogen and 25% helium by mass, were written into its bones. No stars had yet formed, no galaxies had coalesced, and yet the raw material for all future structure had been set. It's as though the cosmos, before taking its first full breath, had already decided what kind of body it would build. What makes this moment more than poetic is its precision. When physicists ran the numbers, the predicted ratios of hydrogen and helium matched exactly what astronomers later observed in the oldest, most pristine gas clouds. This wasn't just a satisfying coincidence, it was confirmation. The universe hadn't just started, it had started with rules, with logic, with elegance. The Big Bang Theory didn't merely describe the shape of space or the behavior of galaxies, it predicted the very makeup of matter itself, and got it right to within fractions of a percent. And that's the power of science at its best. It takes what seems unknowable, the beginning of time, the birth of atoms, and translates it into something testable, observable, tangible. In the afterglow of the Big Bang, we found not chaos, but clarity, not randomness, but a story with structure, and embedded in that structure, the building blocks of all that would follow. Because those light elements, simple as they were, would become the foundation of complexity. Hydrogen would gather, compress, ignite, and give birth to stars. Stars would burn hydrogen into helium, and helium into carbon, oxygen, nitrogen. In death, they would scatter these elements into space, seeding the cosmos with the ingredients for life. But none of that could have happened without this first act, without the pure, primordial creation of hydrogen and helium, an echo of simplicity that would, in time, give rise to minds complex enough to ask how it all began. It is strange, isn't it, that from the wildest heat ever known, we got something as gentle as water, that from a blinding instant of radiation, we got the matter that would one day become trees and lungs and oceans and eyes. But this is the way of the cosmos. It creates possibility through fire. The atoms that now dance in your blood were forged not in ancient stars, but in a universe still waking up. You are, quite literally, older than the stars. So when we look up, when we trace the path of light back through time, we are not merely seeing stars. We are seeing ourselves, our origin written in hydrogen, our destiny shaped by helium, our presence sculpted by forces that knew nothing of us, and yet made us possible. The universe, in its first few minutes, didn't just begin, it built. It built the lightest pieces of matter, yes, but also the heaviest questions. And those questions now reside inside us, asking again and again, how did this happen? Why does it feel like it matters? And what came before? But before those questions were asked, there was only fire. Fire and the quiet, precise art of becoming. Some memories are so deep, so ancient, they no longer speak in words but in whispers, faint, cold, and all-encompassing. The universe has such a memory. It is not found in stone, nor scripture, nor story. It's in light, a glow so old it predates stars, so constant it touches every corner of space. This is not sunlight, not starlight. It is first light, the final cry of a fire that once engulfed all of existence, and though it has cooled for nearly 14 billion years, it still speaks. If we listen carefully, this echo becomes a map, a message, a fossil, the universe's first memory, still burning. When the universe was just 380,000 years old, it transformed. The seething plasma cooled, electrons calmed down, atoms formed, and in that single moment, brief, quiet, and profound light was set free. Not one beam, not a flash, but all the light. Billions upon billions of photons unleashed across the expanding cosmos. no longer trapped by the chaos of matter, finally free to move. That radiation has never stopped traveling. It passes through everything, around galaxies, through our telescopes, across our bodies. It is the oldest light we can ever see, and it is still here. We call it the cosmic microwave background, CMB for short, but that name hardly captures its poetry. This light is not background, it is foundation. It is the afterglow of the beginning, the faded radiation of the hot, young universe stretched across time, cooled down to just a few degrees above absolute zero, and stretched in wavelength to become microwaves. It is everywhere, in every direction, uniform, quiet, persistent, invisible to our eyes, but if we had microwave vision, the night sky would shimmer with a speckled glow. In 1964, two radio engineers stumbled across it. Arno Penzias and Robert Wilson were working at Bell Labs on satellite communications, tuning a large horn antenna when they noticed a hiss steady, unchanging, omnipresent. No matter where they pointed their instrument, the static remained. They cleaned the equipment. They chased down interference. They even removed nesting pigeons from the antenna. But nothing helped. The hiss stayed. It wasn't noise from Earth. It wasn't a malfunction. It was coming from the sky itself. At the same time, just miles away at Princeton University, a team led by Robert Dick had predicted that if the Big Bang were real, the leftover heat from that fireball should still be here, cooled by expansion, humming in microwave frequencies. When the two teams connected accident and theory finally in sync, the hiss became a signal. The signal became a discovery, and the discovery became a revelation. We had just heard the echo of the Big Bang, but the CMB is more than confirmation. It is a map, a perfect snapshot of the universe, as it was at the moment it became transparent, and though it looks smooth at first glance, it isn't. It's dappled with minute fluctuations, tiny variations in temperature, 1 part in 100,000. But in those faint ripples lie the blueprint of everything. These are the quantum tremors of inflation, stretched across the sky, magnified by gravity, etched into light. Each brighter or darker spot in the CMB tells of a region just slightly denser or thinner than average. Those tiny differences would become the seeds of all future structure: galaxies, clusters, stars, you. Later missions would bring this picture into focus. COBE gave us the first blurry glimpse, then WMAP refined it, mapping the anisotropies with unprecedented precision. Then came Planck, a telescope launched into space by the European Space Agency, measuring the temperature of the sky with exquisite detail, revealing the full fingerprint of the early cosmos. These were not artistic renderings, they were data, the most ancient data in existence, a direct image of the universe when it was younger than a human lifetime. But the story did not end there. The 21st century gave us a new eye, the James Webb Space Telescope. This giant infrared observatory peers through dust and time, rewinding the cosmic clock back to just a few 100 million years after the Big Bang, and Webb was surprised. It found remarkably mature galaxies in a universe still impossibly young, with complex structures forming far earlier than expected. It revealed that the Epoch of Recombination, when the first stars reignited the cosmos, may have begun sooner, fiercer, and more complex than we imagined. This does not erase the Big Bang. On the contrary, it reinforces that the universe truly had a fiery beginning, while forcing us to rewrite the history of galaxy evolution. The Big Bang remains secure. It is only the earliest chapters after it that have become richer, more layered than we once believed. And the fit was astonishing. The statistical patterns in the CMB matched the predictions of inflation and the Big Bang with near perfection. Peaks and troughs, hot and cold spots, all aligned with a theory born from equations scribbled decades before. It was as if the universe had left behind a birth certificate written not in ink, but in energy. A photograph, a record, proof that this vast cosmos we now observe really did emerge from something infinitely small, infinitely hot, and elegantly ordered. But beyond the numbers, there's something more, something almost spiritual. The knowledge that every square centimeter of the night sky carries this ancient light, that when you look into the darkness, you're not looking into emptiness, you're looking into memory. That even now, the same photons that escaped during recombination are still arriving, washing over you, as they have washed over every person who has ever lived. The echo of the beginning surrounds us always, and this light carries more than temperature. It carries symmetry, harmony, purpose. It tells us the universe was born not in chaos, but in calm, that from randomness came rhythm, that even in the earliest moment when space itself could barely hold form, the seeds of balance, structure, and life were already sown. It tells us that we are not separate from the cosmos. We are made from its light, cooled, condensed, evolved, but still echoing. You don't have to understand the math to feel it. Just stand under the stars and know the cold hum of the microwave sky is still there, and it is the oldest sound you will ever hear, the oldest light you will ever see, the purest truth the universe has ever spoken. Imagine a sky without stars, not because they've faded, but because they've not yet begun. A universe that has cooled, calmed, and cleared, but remains eerily blank. The light from the beginning still hums across the sky, but nothing new shines. It is a silence, not of absence, but of waiting. The darkness is deep, yes, but not empty. Hydrogen and helium drift in vast clouds, invisible and unformed. Gravity works patiently, slowly weaving threads of tension. And in that quiet pressure, something ancient begins again. Collapse, heat, fusion. One by one, the stars return not as memories, but as fire reborn. And with them, the universe learns to shine. The cosmic microwave background had passed, the fog had cleared, and yet for hundreds of millions of years, nothing new was visible. The universe had grown cold and dark, filled with simple atoms but devoid of light sources. This was the long night, the cosmic dark ages, a stretch of time where the laws of physics continued to work in silence. No stars pierced the void, no galaxies had yet assembled. The light that bathed the early universe had been set free, but nothing else had yet taken up the flame. Still, the groundwork was already laid. The ripples, seeded by quantum uncertainty, stretched to vastness by inflation, and preserved in the CMB, had formed a cosmic scaffolding. These weren't visible structures, but gravitational fingerprints, denser patches of matter that would begin to gather the gas around them. Over time, these regions began to deepen, pulling hydrogen and helium into tighter clumps. The process was slow, the universe was expanding, and the density was low. But gravity is persistent. It waits, it builds, it collects. Eventually, in the deepest wells of matter, the pressure became too great. The clouds of hydrogen collapsed, ignited, and burned. The first stars were born. They were unlike anything we see today, massive, volatile, unrestrained, hundreds of times the mass of our sun, burning millions of times brighter, and living only a few million years before erupting in supernovae. These were the population 3 stars, born of pure hydrogen and helium, unpolluted by heavier elements. They lit the sky like torches in a cathedral, searing holes into the darkness, ionizing the surrounding gas, and kick-starting a transformation across the cosmos. Their light marked the end of the Dark Ages and the beginning of the Epoch of Reionization. With each new star, more of the hydrogen fog was broken apart by ultraviolet radiation, allowing photons to travel once more. Regions around these ancient giants became transparent bubbles, growing, overlapping, merging until finally, the entire universe was luminous again. Not all at once, not everywhere, but gradually, inevitably, the sky reopened, the silence was broken. But these stars did more than shine. In their fiery hearts, nuclear alchemy began. Hydrogen fused into helium, helium into carbon, carbon into oxygen, and nitrogen and iron. These elements unknown, in the early universe, became the seeds of life and complexity. When the first stars died, they exploded, scattering their ashes across space. Those ashes became new clouds. Those clouds birthed new stars, smaller and more stable, surrounded by disks of gas and dust. From those disks, planets formed. And from some of those planets, Eventually, eyes would evolve to look back at the sky and wonder how it all began. In this way, the death of the first stars gave life to everything else. They were cosmic martyrs, burning quickly so that others could burn longer. And from the fragments of their violence, the next generation of stars, population 2, formed in great numbers, gathering into clusters, spiraling into galaxies, weaving themselves into the filaments of the cosmic web. The universe was not just lit now, it was structured. It had shape, depth, form. Galaxies were the next great creation. Pulled together by invisible threads of dark matter, they spun into being whirlpools of gas and gravity, birthing billions of stars each. Some merged, others danced, and in their cores, supermassive black holes awakened. The sky began to fill not just with pinpoints of light, but with systems, with architectures of fire. The cosmic web was now fully aglow, stretching across billions of light years, connecting galaxy to galaxy with threads of history and heat. And through all of this, the original light from the Big Bang, the CMB, continued to travel, cooling and dimming, but still present, still whispering. Now it passed through a very different universe, one filled with starlight, metal, gravity wells, and complexity. But that ancient light still touched everything, illuminating not just space, but story. From total darkness, the stars had returned, and in their return they brought time to life. Because light is not just a way of seeing, it is a way of measuring. With the first stars came the first clocks, solar rhythms, orbital patterns, cycles of fusion and decay. The universe could now be marked not just in temperature or density, but in days, years, lifespans. Time became personal. Today, we look back and see that moment of illumination not as distant, but as defining. Everything we are, our chemistry, our biology, our thoughts can be traced to the deaths of those early giants. The calcium in our bones, the iron in our blood, the oxygen in our lungs, all forged in stars that lived and died before the Earth was even a thought. To say we are stardust is not poetry, it is diagnosis, it is lineage. And so the darkness was never final. It was only the canvas, the silence before the music, the breath before the flame. What does it mean when math and the stars begin to agree? When numbers on a chalkboard start reflecting the patterns in the sky? When human-made machines, orbiting in silence above the Earth, begin decoding whispers from the dawn of time? It means the universe is not just beautiful, it is knowable. That chaos contains pattern, that mystery contains memory, and that the fireball from which we came has not stopped speaking. It speaks in data, in radiation, in ratios and redshifts and relics. And from these clues, scattered across sky and sensor, we have learned to reconstruct the birth of everything. The first clues were subtle. Hubble's redshifts revealed that galaxies were running away from us, not because we repelled them, but because space itself was expanding. That was the first hint, but a single hint does not tell a story. So science waited for more, and more came not from one place, but from many, from the color of distant galaxies, from the ratios of helium to hydrogen in deep space, from the static hiss detected by satellites and antennas, from cosmic background maps so precise they look like fingerprints. Slowly, a picture emerged. It wasn't a painting, it was a photograph, a thermal image of the infant cosmos. The cosmic microwave background gave us that. First with COBE, which proved the universe had the exact blackbody spectrum predicted by the Big Bang. Then with WMAP, which showed us the temperature fluctuations with razor clarity. Then came Planck, whose observations were so precise, they effectively froze the baby picture of the universe into a frame we could never again unsee. The fluctuations, the cold spots, the peaks and troughs, all matched predictions made by physicists decades before. And the match was breathtaking. Not just approximate, not just close, exact. The patterns in the CMB lined up with inflation theory, with Big Bang nucleosynthesis, with redshift data. The early universe wasn't just hot, it wasn't just dense, it was predictable, and we had predicted it. Scientists weren't merely guessing, they were listening, and the universe was telling them they were right. What this meant was astonishing. We could now know things we could never observe directly. We could describe the conditions of the universe when it was less than a second old. We could tell how many protons formed per cubic meter. We could even measure the geometry of space itself and find within a tiny margin of error that the universe is flat, not bent, not curved, not closed like a sphere or open like a saddle, but balanced, flat like an infinite sheet of paper. The implications of that are profound. It suggests that inflation didn't just stretch the cosmos, it smoothed it. It left it in perfect equilibrium. And from that equilibrium, new mysteries emerged. Because with each layer of understanding comes a deeper question. The data doesn't only answer, it also whispers what is missing. For instance, the CMB tells us that only about 5% of the universe is made of ordinary matter. Everything we can touch, taste, burn, build. The rest, dark matter and dark energy, unknowns. Forces we can measure only by their effects, not their essence. Something is holding galaxies together, something else is pulling them apart, and both are invisible. These aren't gaps in imagination. They are features of the data, unseen, yes, but undeniable. We also learned when the first stars formed, when the first galaxies came together. We learned how long the Dark Ages lasted. We learned that the universe is 13.8 billion years old, not by counting backwards like children on a timeline, but by reading the sky's temperature like a doctor reading a pulse. The light tells us, the matter confirms it, the background sings it, and then came the gravitational waves. Einstein had predicted them a century earlier, ripples in space-time itself, but for decades, they remained a dream. Then in 2015, the Laser Interferometer Gravitational Wave Observatory, LIGO, heard one. Two black holes colliding in a distant galaxy, shaking space-time so subtly that only the most sensitive instruments on Earth could notice, and they did. The detection opened a new window, not just a way of seeing the universe, but of hearing it. The universe now had sound, but what scientists dream of next is even older: primordial gravitational waves, the ones that might have been born during inflation. If detected, they would be direct evidence of the universe's first tremors, quantum jitters writ large. We've looked for them. In 2014, a South Pole telescope named BICEP 2 announced a possible detection. It was thrilling, and then it wasn't. Dust, galactic interference. The signal was not pure. The celebration paused, but the search continues. If we ever do hear that deep whisper, it will be the closest we've ever come to eavesdropping on the birth cry of the cosmos. Still, even without that whisper, we are deep in knowledge. We know the universe is expanding faster today than in the past, thanks to something we call dark energy, another mystery riding on Einstein's equations. We know galaxies are flying away from us at ever-accelerating speeds. We know the observable universe stretches more than 90 billion light-years across, even though it began from a volume smaller than an atom. And most miraculously, we know it tells the truth. The story it tells over and over, across every method, every wavelength, every discipline, is consistent. The light confirms the math predicts the structure echoes the origin. It is not a myth, it is not a metaphor, it is a memory, a scientific memory the cosmos has chosen never to forget. And we, curious beings made of carbon and stardust, have become its listeners, its translators. We build machines to catch ancient light. We build equations to chase the earliest seconds. We stare through the noise of now to glimpse the clarity of then. And what we see, again and again, is that everything we are was once written in fire. What if our beginning was not the only one? What if the Big Bang, the greatest story ever told, was merely a page in a larger book? Imagine a cosmos where universes bloom like fireflies in a forest at night, each with its own space, its own time, its own laws, some cold, some curved, some never forming stars, others too brief to last. Imagine this vastness beyond vastness, a realm where our entire observable universe is but one shimmering bubble in an infinite cosmic foam. This is not science fiction. It is the logical edge of science itself, and it is where cosmology dares to dream. Inflation, the theory that the early universe expanded faster than the speed of light for a fraction of a second, has solved many puzzles. It explains why the universe is so flat, so uniform, so vast. But it has also opened a door we cannot unsee, because in most models, once inflation starts, it doesn't stop everywhere at once. It ends in pockets, in patches, in regions. One bubble stops inflating and becomes a universe. Another keeps going, then stops, then another, and another. Each one, its own cosmos, sealed off by stretching space, unreachable from its neighbors. The result is staggering. A multiverse, born not of imagination, but of equations. In this picture, our universe, the one we see, measure, and live in, is just one bubble in an ever-expanding foam. Eternal inflation never ends. It is always inflating somewhere, and as it does, it buds off new universes, some perhaps like ours, others wildly different physics, different particles, different possibilities. There could be universes with no gravity, universes with no light, universes that collapse moments after they begin, or universes teeming with complexity we cannot fathom. This isn't fantasy, it's mathematics unleashed. And while we can't observe these other worlds directly, they lie beyond our cosmic horizon. There may be traces, subtle clues. If another universe ever collided with ours, it might have left a scar in the sky, a circular anomaly in the cosmic microwave background. Scientists have searched for such patterns. Some have claimed hints, others remain skeptical. The data is messy, but the idea remains tantalizing, that we might one day find evidence not just of a Big Bang, but of other bangs, other birthplaces, other dreams of matter and time. This view of eternal inflation changes everything. It means that our universe is not the whole story. It means that our Big Bang wasn't the first and won't be the last. It reframes our uniqueness. We are not a privileged creation, but a statistical outcome, a consequence of quantum fluctuations and runaway expansion. And yet, doesn't that make us more precious? In a multiverse of endless possibility, to be a universe with stars, with chemistry, with eyes that ask questions is a miracle made meaningful by rarity. But inflation isn't the only path to other universes. String theory, a leading candidate for a unified theory of physics, offers another route. In some versions, the Big Bang was not the absolute beginning, but the result of a collision, not of particles, of brains vast, higher dimensional membranes floating in a higher dimensional space. Imagine two sheets of cosmic fabric drifting in a larger void. When they touch, the energy released creates a universe, our universe. The Big Bang becomes not a point, but a collision. And just as waves ripple through water after a stone hits the surface, our cosmos ripples out from that impact, filled with energy and expansion. In this picture, there may have been a before, a time when the brains drifted, a space beyond our space, time beyond our time, other brains, other collisions, other bangs, and perhaps even cycles, because some theories go further still. Nobel laureate Roger Penrose has proposed conformal cyclic cosmology, an idea where the universe doesn't end, but resets. In this model, each universe, each aeon, expands eternally until matter fades away, until only radiation remains, until time itself becomes meaningless again. And from that timeless end, a new Big Bang begins. One universe begets another, again and again and again. The Big Bang is not a beginning, but a transition, an eternal rhythm of creation. If true, our cosmos is part of a cosmic ancestry, stretching backward and forward without end. Perhaps we are not the first to ask these questions. Perhaps intelligence rose in a previous eon, stared at its stars, wondered what came before, and then was swept away by expansion, only to leave the stage for us to ask the same. And some theories are even simpler. They suggest that our universe sprang from a quantum fluctuation, that from a timeless quantum vacuum, a nothing that is not truly nothing, a bubble of energy tunneled into being. It didn't emerge in time, it brought time with it, and space, and law. In this view, even nothing is pregnant with potential. The Big Bang becomes not the moment of creation, but of realization. The moment the universe became something rather than the undifferentiated sea of probability it was before. These are not just philosophical musings. They are serious attempts to answer the hardest question we know: why is there something rather than nothing? Why does the universe exist at all? Science may never fully answer that, but it can offer pathways. It can point to models, to predictions, to patterns that suggest we are not an accident but a consequence. Not alone, but part of something larger: the multiverse, the brain ocean, the eternal cycle, the quantum foam. Whatever the truth, one thing is clear. The Big Bang was not the end of the mystery. It was the beginning. And as we trace its echoes across the sky and through our equations, we are forced to consider something even greater than everything we know. That our story, our universe, is just one verse in a cosmic poem still being written. Some answers end the search. Others open doors we never knew existed. The Big Bang is one such answer. It gives us a beginning, a moment, a mechanism, a map. But at its edge, we encounter something stranger: the breakdown of knowing itself. What came before? What lies beyond? The equations tremble, time dissolves, causality curls into paradox, and we are left not with facts, but with questions that pulse like stars behind clouds. What is time? Why does anything exist? And what does it mean when gravity itself can repel instead of pull? The deeper we look, the more reality becomes reflection. At the core of the Big Bang story lies a contradiction. It is both the most comprehensively understood event in all of cosmic history and the most mysterious. We can describe what happened after the first trillionth of a second with astonishing precision, but what happened at that first moment? Our mathematics fail, our concepts shatter. The Big Bang begins as an elegant theory and ends as a singularity, a place where time, space, mass, and energy become infinite, and our models yield nothing but riddles. In physics, a singularity means the laws we trust can no longer guide us. It's not just a blank page, it's a page where the ink refuses to stick. We see this too at the center of black holes, those collapsed stars whose gravity traps even light. There, as in the Big Bang, our understanding unravels. Is it the end of meaning? Or the beginning of something we haven't yet discovered? Perhaps it's not the universe that ends at the singularity, but language. Because the moment you ask, what came before the Big Bang, you're using a word before that assumes time already existed. But if time began with the universe, then the question breaks its own grammar. Before implies a clock, but the clock had not yet been wound. In this light, the Big Bang is not just the origin of matter and energy. It's the origin of sequence, of cause and effect, of history. Before it, there was no when, and that shatters our intuition. We are creatures built on time. We measure our lives in heartbeats, sunrises, years. We think in past and future. But the Big Bang tells us that time is not absolute. It was born, it flows, it bends, it may even stop. Some theories suggest time could end in the far future. Others say it might cycle. And some whisper that time itself is just a construct, a shadow of deeper patterns we can barely perceive. Then there's gravity, the force we thought we understood. For centuries, gravity was attraction. Apples falling, planets orbiting, stars collapsing. But Einstein showed us it's more than that. Gravity is the shape of space-time itself. Mass tells space how to curve. Curved space tells matter how to move. And when the equations are pushed hard enough, strange things emerge. Gravity can reverse. It can push. This is not speculation. It's built into the math. It was Einstein, after all, who first added a cosmological constant to his equations to allow for a static universe, a term that today looks suspiciously like dark energy, the very force accelerating the universe now. The force that likely powered inflation then. Repulsive gravity is real. It exists in the early universe and in its distant future. It stretches space itself. But why should gravity repel? Why should nothing be unstable? Why should the universe be here at all? That last question is the most haunting. Why something rather than nothing? It echoes across science and philosophy alike. Some physicists offer answers: quantum fluctuations, vacuum instability, probabilistic emergence, and yet every how answer seems to circle back to a why. Why these laws? Why these constants? Why this recipe that leads to stars, planets, life? Science, in its humility, often steps back here. Its job is to ask how, not why. But for us thinking, feeling beings, the why persists like a song stuck in the mind. We want to know if this all means something. The Big Bang invites us to shift perspective, to understand that asking why may be asking too much of nature, or perhaps too little of ourselves, because meaning isn't something the universe owes us. It's something we create when we reflect, when we marvel, when we build telescopes, write equations, whisper to the stars, and dare to imagine that this fire of existence might contain not just facts but purpose. What we've learned is astonishing. The universe did not need divine intervention to ignite. No finger reached from beyond to light the fuse. The laws themselves are enough laws we can describe, test, predict. The Big Bang didn't require a miracle. It was the miracle. A miracle of law, of mathematics, of symmetry, broken and reborn. And yet, within that cold precision lies something deeply human: awe. Awe that we can trace our atoms to stars, and our stars to the breath of the beginning. Awe that from silence came sound, from darkness came light, from chaos came consciousness. Awe that a species on a pale blue dot could reconstruct the first seconds of everything. In the end, the Big Bang is not just a theory, it is a mirror. It reflects our hunger for truth, our defiance of ignorance, our belief that understanding is possible, and that understanding in itself is a kind of transcendence. What does it mean to live inside a memory? To breathe the remnants of a beginning so ancient it predates the concept of age? What does it mean that the stars remember where they came from, and that we born of those stars are capable of remembering too? Not just remembering, but decoding, telling the tale, singing the fire back into form. We are not outside the story. We are not even separate from the beginning. We are what the Big Bang has become: curious, conscious, and reaching for the light that never left. In understanding the cosmos, we are remembering ourselves. Every time we look at the night sky, we are peering into time. The starlight that touches our eyes tonight began its journey long before our ancestors spoke language. The galaxies we observe are frozen portraits of youth, aging across distance, painted in photons and memory. The deeper we look, the younger the universe appears, until we reach the faint microwave glow of the Big Bang itself, the last light of the first breath. This light is not just a symbol, it is evident. It tells us that the universe began hot and dense, then expanded and cooled, structured itself into galaxies, birthed stars, forged elements, and eventually assembled planets capable of thought. That's not poetry, that's physics. And yet, it feels like poetry, doesn't it? Because the facts are more than just fact. Their origin, their belonging. Carl Sagan once said, "We are made of star stuff," but even that feels modest. We are made of Big Bang stuff. The hydrogen in our water, the oxygen in our breath, the calcium in our bones, the carbon in our skin, all of it traces back, not just to stars, but to the moment stars became possible, the moment matter condensed, the moment light escaped, the moment the universe blinked into visibility and said without words, "It has begun." And now, here we are, living on a small world orbiting a mid-sized star in one galaxy among hundreds of billions, wondering how we got here and somehow knowing that the universe is 13.8 billion years old, knowing that space is expanding, that galaxies are fleeing, that the past still glows faintly in microwave static, knowing that everything we see was once compressed into a volume smaller than a proton, knowing that, from silence, came symphony. And what do we do with this knowledge? We build, we explore, we argue, we write, we wonder, we love, and we tell stories rooted in physics, shaped by philosophy, animated by imagination. The Big Bang is not just a theory scribbled on blackboards or buried in telescopes. It is a narrative, a cosmic epic in which every person, every moment, every breath is a continuation of that very first line. In the beginning, the story has evolved. It now includes inflation, dark matter, dark energy, multiverses, quantum fluctuations, gravitational waves. Perhaps, in time, it will include even more dimensions beyond our own, echoes from previous universes, whispers from brain collisions, or messages embedded in the curvature of time itself. But even if it changes, even if the edges blur, the heart of it remains. The universe had a beginning, and that beginning can be traced, tested, and above all felt, not in equations, but in awe, because awe is what remains when science touches the soul, when we stand beneath a canopy of stars and feel their distance not as cold, but as history, when we realize that the atoms in our hands were once inside a star, and before that, inside a glowing soup of newborn matter, and before that, folded into a singularity beyond comprehension. When we whisper, "How can this be?" and the universe whispers back, "Because it island." And in that moment, something happens. We stop being observers, we become participants, not just in the universe, but of it, not just in the story, but as the story. We are the cosmos aware of itself. We are the universe remembering its fire. We are the echo of creation made flesh, made thought, made wonder. This is the true gift of the Big Bang, not just that it happened, but that we know it did, that we can look up and out and in and see the same truth unfolding in every direction, that from a singular point of infinite possibility came everything: time, space, light, law, life, thought, us, and that even now, across this vast and expanding cosmos, the fire still burns. It burns in stars, it burns in data, it burns in the questions we ask when we look into the dark and feel something ancient calling back. In the beginning, the universe was born, and now through us it has begun to understand.